All right, so it is Monday, June 6, 2017, and I'm actually sitting here at MIT. I'm on the fifth floor of the MIT Athena cluster, and it's changed a lot. I mean, over here is a little sort of a Connect 4 or tic-tac-toe for kids. There's a nice fishbowl back here, some plants, and I don't know, a lot of familiar things, but a lot of new things here at MIT as well. So, unfortunately, it looks like the Grace Center students have maybe given up on me because it's 11:30. Oh gosh, it's 11:30 here, so it's 9:30 a.m. in Montana, and what would that be? 10 p.m. in Sri Lanka, so probably a little too late to be hanging out. But I'm going to go ahead anyway and cover the battery quiz. It looks like the recording is going just fine, and I've got good audio. I apologize for the background, but let's go ahead and move forward on the battery quiz. I also just want to let everybody know we're working on getting a curriculum going for the Blackfeet Community College. I have put together, let me get into courses, BCC. I've put together proposals to teach 101 and also 242 in Browning this fall, and we'll offer those online, so looking forward to that. And I think what we could probably do, moving forward is just set up our own courses, our own blogs, independent of the University of Montana and Missoula College, and just at this point I want to officially acknowledge and thank the University of Montana and Missoula College, and the leadership of Paul Williamson, the leadership of Tom Gallagher, of Ashley Preston, also Brian Kearns for helping us launch the Renewable Energy Technology program at the University of Montana. I'll go back out here. Here's, the website's still there, and I guess I'm still the director, but this not really clear how much longer this will be active. What we will do, though, is take all this great legacy that we put together over the last decade. So the program is moving into its second decade. It was established in 2006, 2007, with several grants, some from the Montana Department of Commerce, some from the Department of Energy, really to move Missoula and Montana away from the carbon economy and towards a hydrogen economy. And like a lot of inventions, you have to have a good idea. You have to be, the idea has to occur at the right time, and it has to occur in the right location. And I think in a lot of ways the renewable energy technology program, great idea, maybe not the right time and space being there in Montana 10 years ago, but we'll keep moving. We're now global. We're online. We're teaching in Sri Lanka, and as well as at the tribal nations in Montana, and I know a lot of them are keenly interested in moving off of the extractive carbon economy. So with that in mind, let's get into batteries. So here's courses. I also really want to thank John Bailey for enabling this, and also want to thank Naresh Gatharian. And I'm sorry, Naresh, I probably butchered your name there, but thanking Dr. Naresh for allowing us to have this opportunity. All right, so let's get into, and it's just amazing to see all of these courses that we put together at the University of Montana, and these will all be archived and available. One other thing that is also worth noting, sitting here at MIT has made all of its courses available online. You can't necessarily earn the degree that way, but this information and knowledge is free. Now, if you've got electricity and a computer, you can have access to all this great information, data, ideas, etc. All right, so let's go into the battery quiz. And so we've gone over watt versus watt hour. We've gone over basics of electricity. We've gone over the timeline of solar. We've gone over sort of the curriculum review. We've done cells, modules, and arrays. We did inverters last time. So I'm just going to go through these guys, and I'm going to call this, I'm going to rename the batteries as 6. So there's the battery quiz. There's 4 questions there. There's also the batteries exam, and there's 17 questions there. So we'll go over both of those. We'll go over both of those today. All right, so let's go over the quiz first. Battery quiz solution, and I'm just going to dive right into the solutions. Okay, so first question, it is unwise to add new batteries to an established bank. And the answer here is D. The answer here is D. And the reason for that is that if we have, and I'll bring up a little shot of batteries in parallel. Let's look at some images. Okay, so here's the reason, one of the main reasons for not adding it. So if this is 12 volts, 12 volts, 12 volts, if you add a new battery, this battery, for example, might be at a lower voltage. And if that's a lower voltage, instead of current flowing through the load, the current can sometimes flow through the battery. And this is bad. It's a drain on the system. It's a drain on the system. It makes it work improperly. You could put a diode in here so electricity only flows in one direction, but adding batteries to a bank that aren't at the same voltage is typically a bad idea. They should all be at the same age so that they're the same charge, the same voltage. Okay, so the answer there is D. All right, to increase battery voltage, this has to be done in series. This has to be done in series. And let's take a look there. So in this case, these guys are in parallel. So 12 volts, 12 volts, 12 volts. Everything is still 12 volts. The current adds, though, in this way. So 1 amp plus 1 amp plus 1 amp is 3 amps. Here's another one. Yeah, so if these guys, okay, look at these. So these are batteries in series. 12 volts goes here, another 12 volts, you get 24. So in parallel, the voltage stays the same. In series, the voltage adds. So that's the answer to that question. So let's see. And then 3. To increase battery capacity, you have to use bigger cells. And you put more of them together in parallel. You put more of them you put them in parallel. Again, if we go here, we can see in parallel, you have 1, 2, 3, 4. It just makes a larger battery overall, and that will give us more amp hours if we put more batteries in parallel. Okay. This one, series connection. A series connection is always positive to negative. That's correct. The electrons have one path. Yeah, I'll buy that. That sounds good. And then I don't know what happened here, but anyway, what they're looking at are ways that, so corrosion, this can happen at terminals if the battery leaks, excessive gassing, excessive basking. Ask the battery doctor. Who's the battery doctor? Well, he's right there, Andrew McChain. We'll have to go ask him. I don't know the answer to that question, but he will. It's one of my graduates. We'll ask the battery doctor that question. Premature battery failure. I'll just say this is from poor maintenance. Explosion and fire. This can happen if batteries not well ventilated. Okay, so that's that quiz. All right, so that's the batteries quiz. Now let's go ahead and get into the battery exam. Battery exam. Battery quiz, battery exam solutions. All right. Okay, blank is the amount of time a fully charged battery system can supply power to system loads. This is the capacity. So more capacity, you get more time. To prevent sulfation or sulfur. Okay, rapid charging of batteries to full charge is the best way to prevent and help reverse sulfation in batteries. Again, I don't think rapid is the right answer. Let's just say regular. Regular. And consistent. Okay, so there's that. D. Stratification comes from undercharging. Okay, undercharging. You've got to keep the batteries full. And then for this one, I suggest, there's some great papers out there. Let me show you someone. Yeah, so this is, let's see what's out here. Let's just see what she's got here. Let's see what she's got. This is the old archive. This was some of my stuff here. Page, publications. Publications. Extract full length. 2011. 2011. 10. Yeah. You know, here's an example. Porous cathode optimization. Here's another one, numerical simulation, electrochemical society. So this is another good set of books, or a good journal to look at for this type of stuff. Let's go back. 2007. Somewhere down here. Oh, there's one of my papers right there. Cool. All right. Well, I'm glad to see that stuff is still up on the website. Hasn't been updated in a while, but still there. Still there. Interested to see what some of these other things are. We should look this guy up. Let's find this. 101 of the few perceived joules. Advanced battery sulfur list. Let's see.
Can you hold on to like 5 minutes?
This is fun reading. This is fun reading. Oh. That's okay. How are you? Oh, it's very late there.
Yeah.
You should be in bed. Oh, no, it's my fault. I was very late. I had a meeting. I had a meeting with a computer group, so I'm sorry I'm late. Good morning. I was reviewing the batteries quiz, and I got a little bit distracted because I've been reading some news about my doctoral advisor, and let me show you where I am. So I'm going to share the screen. Share screen. Somebody's dog. Oh, that's nice. Is that a doggy back there? No.
Yeah.
Oh, okay.
Yeah.
That's nice. I miss my dog. Okay, so I'm sharing my screen, and here's where I was. I've done this. I've done the batteries quiz. So I finished this. I finished the batteries quiz, and I was moving on to the batteries exam. And I was going through question number 3, and reading through this question made me think of my advisor. So let me show you my doctoral advisor. Her name is Anne-Marie Sastry. So this is a picture of my advisor. This is her. She's sitting here having a meeting, and she's done a lot of work in battery technology. This and this is a video of her meeting with Barack Obama. I'm just going to show this really quick.
tried to solve the light bulb by getting into a very, very high energy density battery cell. We still make it on a very scaling product. And the match, so we're simulations people by origin, and so we started doing some simulations, calculations, and determined that we believe the best way was to have an all-solid-state, non-liquid electrolyte. And so we started making batteries on equipment that we bought on eBay that was very cheap. It was used to make things like food packaging. And last summer, we demonstrated over 1,100 watts, and about double what's available in the marketplace.
You don't tell me about this. It's Coastal Ventures. So.
Yeah, we did our series.
Yeah, I know. So,
Everybody get a picture of the President of the United States with her.
they take a bunch of pictures. So, this particular battery technology applications for everything from cars to devices to.
That's right. Yeah, we just had an investment from Dyson, and so we first put our batteries in their products, computers, and consumer electronics, and so forth. And after that, was fascinating. The reason we started the company was to get into electric vehicles. That's been a passion of ours for a long time.
How do we cut the cost and size and longevity? That's our big stumbling block, driving down the price point on electric cars.
Yeah.
So have you solved it?
We believe so.
Okay.
We have to scale it up,
Right.
and but this was after working on the incumbent technology for a long time. My team and I came to the University of Michigan. I was a professor there for 17 years, and so I came out of my laboratory. And a surprising thing happened. The first little prototype we made at U of M worked, and it was based on NSF funding. So we decided to start a company, and it's true.
That's great. And what are the barriers to scaling up? What are the things you still have to figure out in terms of being able to, for this to then become the standard bearer for batteries?
The usual engineering work. Every time you make a larger cell, you deal with the flaws, you have to make it faster, you get bigger equipment, pieces of equipment, you make them at a higher rate, and so we go through all those development steps, then you have to stop and test, and then build again and stop and test.
Excellent. Well, I'm very excited. Let's get it done. Come on. Where? But are you getting the, okay. Because you can tell I was in trouble with ours. When I picked up the batteries.
I had to get one of those. Thank you. Happy birthday.
Okay, everyone saw that?
Yeah.
Okay, so that woman, she was my doctoral advisor at University of Michigan. So she's done a lot of research with small batteries, and what she was explaining to President Obama is she was trying to take the batteries and make them larger. So one of her students used the battery in a cochlear implant for a hearing aid in your ear. But the next step, but I think if you see this website, the next challenge is to put the battery in a car, which is more challenging. So anyway, I have a little bit of background. Most of my work at her lab, it was not with batteries, it was more with biological materials. And this picture you see here was one that I took with another graduate student. But a lot of simulations, a lot of experiments to try to move renewable energy storage forward. Okay, well, I just wanted to share that with you because that's part of my past and perhaps part of all of our futures. Okay, so back to the exam. So question 4, if a second identical string of 4 6-volt batteries is wired in parallel, what is the nominal voltage and capacity. So let's see, so we have 6 volts. I'm just going to do this problem with the notepad. So what we have is we have 6 volts. Okay, if the second identical string of 6-volt batteries okay, so let's just cheat a little bit and look at the answers. So we know 24 volts is F and B is 800 amp hours. So how do we get that? So if we have 6 volts, here's another one, 6 volts, another one, so if we have all of these wired, so tools, pen, if we go in here, then out, then in, then out, then in, then out, so from this plus to this minus, we have 24 volts. 24 volts total, because we have 6 plus 6 plus 6 plus 6 all in series. These are in series. And then the total capacity is 400 amp hours. So let's write that. 400 amp hours. And then for this guy, we know that the energy equals volts times amp hours equals 24 times 400 equals, let's do that math really quick. So 24 times 400 equals 9,600. 9,600. This is watt hours. It's very important that we know that it's watt hours, because a watt is a volt times an amp. A volt times an amp is 1 watt. Okay, so that's for one string. Now if we take this, tools, let me see if I can do this. Tools, pen, eraser, edit, selection tool. Now we take this whole thing, copy, paste. Okay, so we have a second system, and we're going to wire this in parallel. Now these two guys are in parallel. And pardon my scribbles, I don't have my pen with me today. We still have, these guys are attached together. These guys are attached together. The whole system is still 24 volts. Whoops. 24 volts from there to there. But we go 400 plus 400. 400 equals 800. 800 amp hours. Amp hours. And the energy equals times 2. Times 2 equals, so double the energy. Good. I think you can follow now. This is good. So 19.2 kilowatt hours. Okay, so we go back to the quiz. So we went from 400 to 800, and then we also calculated the energy. Okay. There we go. All right, so question 5. How many charging amps are required to charge 48 volts, 800 amps? Okay, 800 amp hours. So, and this is at a C20. So, C20 means 20 hours to charge. So almost a day. So if we have the 800 amp hours divided by 20 hours, so 800 amp hours divided by 20 hours is 40 amps. 40 charging amps. So C is the answer, 40 amps. Okay. Because remember, energy is volts times amps times time. Yeah. Okay. This is good. Okay. The next one. The blank is the percentage of energy remaining in a battery compared to the fully charged capacity. And this is just called state of charge, which is B. And that's just a name. You can think of it like this as a picture. You know, of the battery. Of course, the battery doesn't have liquid in it, but you can just say that the battery is partially full. You know, maybe 80%. 80%, let's say. And that's just called the state of charge. State of charge. You know, how full the battery is. Let me make that a little bit bigger. Format text. Oh, okay, 24. Okay, state of charge is how full the battery is. And normally in most batteries you want to keep it greater than 20%. So, greater than 20%. Some batteries you want to go through the full cycle. The full cycle, so this would be, up here is full. Down here is empty. 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 But in general, full is better. And obviously this is as you this is as the battery is loaded. Loaded, L-O-A-D, load, and this direction is charging. Or charging. Okay. This one, blank is an open circuit condition where no electrical is changing. Yeah, I don't know about this one. Yeah, you could call this steady state. That's fine. Steady state would be just this. It's just flat. This is steady state, where the charge equals load. And you know, if you have a cell phone, you know, if you're using your cell phone, I don't know if you can see my picture right now, but if I have here, let me show you. Okay, so if you have your cell phone and it's plugged in and charging, if the charging rate equals the discharge, that's just steady state. So it's a net zero. Okay. Thanks for staying awake. I feel so bad I woke you up. Okay, just a couple more. Okay, back to the quiz. Batteries exam. Okay, steady state. Okay, choose two answers. If four 6-volt batteries are wired in series, what's the nominal voltage? Okay, this one we already know. It's very easy. It's the same solution we just did. Let's go here. All right, so 24 volts. 24 volts. We already did this, right? So 24 volts. And then back to the quiz. Back to the exam. 24 was the normal. And 400 amp hours, that's E. 400 amp hours. Right, so this is that. Okay. That's good. C and E. Next one, what is the open circuit voltage? Open circuit voltage of a fully charged lead acid battery cell. Okay. And here the key is just the cell. Is the cell. Because yes. Yeah? I'm listening. You have a question? Okay. So open circuit voltage of a fully charged lead acid battery cell, it is 1.2 volts. And let me see if I can find this here. So cells in a lead acid battery. Let's just check this out. Ah, very good. Okay, so see, this is a common lead acid battery. 1, 2, 3, 4, 5, 6. And if we go to our calculator, 2.1 times 6 equals 12.6. So it's a little more than 12 volts. So inside the battery, again, this whole thing is the battery. And these are 6 cells inside. And that's what the inside of the battery looks like. Okay. So that's that. Okay, 10. Choose all the correct answers. During an absorption charge.
Uncle,
Yes.
what is the answer to the quiz?
Which one?
Joseph?
The answer to the quiz?
Yeah,
For the battery quiz?
yeah.
Oh, I already recorded that. I'll send you the video.
Okay.
Okay, you'll see it. It's at the beginning of this session, so you'll see everything. Okay, and it's maybe I maybe spend 5 minutes on it, 10 minutes. So, good question. Thanks for asking. I'm very glad you want to know the answer. Thank you. Okay. Okay, so number 10 on the exam, choose all correct answers during an absorption charge. So what it says here is that gassing occurs, and we'll look at that a little bit, and also voltage is regulated at constant voltage. So during charging, let's go look at this a little bit. Gassing during battery charging. Let's see. So let's just see. Charging of lead acid batteries can be hazardous. And so this is what happens. There's some hydrogen gas. And let's look at the chemical reaction. Let's see if we can find it. I want to find the chemistry. Yeah, okay. This is... here we go. Here we go. View image. Okay, so here's what's happening. There's water, and the water can split into oxygen and hydrogen, and it's these electrons that actually move at the positive plate that's causing the charging. At the negative plate, you have lead. So remember, it's lead acid battery plus oxygen makes lead oxide. Over here we have lead oxide plus sulfuric acid, so H2SO4 makes lead SO4. This goes to reaction 1. This oxygen goes there. And then also what's happening is lead SO4 makes 2 hydrogens and 2 electrons. So this is where the gas comes from. You can actually lose some hydrogen. So what has to happen in these batteries, you have to add water. So let me go down here. Tools, insert, text box. We must add water to lead acid batteries because of hydrogen and oxygen gassing. So this is just a result of the process. It's basically waste hydrogen and oxygen, which is kind of strange, but it happens. and we can talk more about that. So I just showed you, this is the reaction. So this is lead, this is sulfur, and these are the electrochemical reactions that happen in the battery. Okay. Okay. So 11, blank is a collection of cells. We already know that it's battery. It's just called a battery. 12, choose all correct answers. And the question is, what is equalization? So equalization reduces stratification. So equalization means that all batteries in a battery array are of equal voltage. Very important. So reduces stratification, reduces sulfation, and is a controlled overcharge. Okay, so it actually goes slightly higher than 12 volts. Slightly higher than 12 volts. This is overcharge. Okay, so A, B, and C, equalization is typically done every 1 to 3 months on solar PV batteries and can be programmed into most charge controllers. So there we go. Very important. So we need to hopefully do a little bit of programming while we're over there in Sri Lanka. Okay, next question. Batteries are a class of batteries designed for repeated deep discharge. And these are called traction batteries. So A is the answer. And so traction, we can go back to this. Traction is where you do a deep discharge. So this is deep discharge. Deep discharge. Again, I'm sorry it's so slow. My pen is broken. Okay. So that's traction battery. Deep cycle. And it can go up to 80%. All right. Next one, blank is an electrolyte that is immobilized. And this is just called captive. And if we go back to in the lead acid, these are not captive. So the point here is that this is solid. Solid, not liquid, like in a lead acid battery. Yeah. So in a lead acid battery, and so lead acid. Let me go back to periodic table. So any element can be used as a battery electrolyte except for these. You cannot use the noble gases. But if we go down here, let's look for Let's look for lead, PB. Let's look for lead. Barium, mercury, thallium, lead. Okay, here's lead right here. And here's, so, heavy metal, very dense. This is what it looks like. It says compounds of lead are usually in the +2. That's why we have lead oxygen. I'm trying to see where it has. This is also bad. It's also highly toxic. It's a neurotoxin. That's why we're moving away from lead as a. That's why we're moving away from lead in batteries. But if it's safe, it's okay. We can go down here. We can try to find batteries. Yeah, right there. So there we can see it's used in lead. There it is, lead acid battery. Very common. Okay, and then the other one's sulfur. That's what sulfur looks like. It's usually very smelly. Let's just see if we can find battery here. So look, you can even have a sodium sulfur battery. I'm surprised they don't mention lead acid battery. Okay. Now, the next one, a blank is a battery that uses a combination of plate designs to maximize the desirable characteristics. So the answer here is hybrid. And I don't know that much about the hybrid battery, but that would be a good little thing to research. Okay, the next one, 16, is a condition of a flooded acid lead cell in which the specific gravity is greater. And this is stratification. And again, this is undesirable. Undesirable. Let's just take a look for it. So this, what they're showing here is that it says acid begins to concentrate at the bottom and the performance is affected adversely. It's better to have a nice homogeneous structure where everything is nicely mixed inside the battery, not some kind of gradient between the top and the bottom. It's better if everything is equal and uniform. Okay, 17. Choose all factors that reduce battery capacity. So older batteries have lower capacity. High discharge rate is also bad for lifetime, and low temperature is also bad. So when the battery gets too cold, the reactions don't happen as quickly. Okay, All right, so we've covered batteries. I'm recording this, so I will, if I went too quickly, I'll send you the link and we can go over it. I think in your systems, I don't think you're going to use batteries that much. I think you'll mainly use inverters, but one thing that I think you might want to look at is how to have maybe a local 12-volt system, for cell phones, because the cell phone is always DC, and so the one thing that might be kind of nice is if you have a local DC 12-volt system, and that way you don't have to have an inverter from going from DC to AC. So I hope that helps. Yeah.
Could we use the same time solar current to the tubs of chili? Or we need to change?
Say one more time. Can you repeat it?
Could we use straightly the solar power to our, now we are using normal current, no? By water regulator. Could we use suddenly the solar power to all the machine?
Yeah. So I understand your question. It's important that you have some kind of charge controller for your batteries, because it's very important for any phone that it be constant 12 volts. 13 is too high, 11 is too low. It must be consistent 12 volts. You need some kind of computer charge controller, and we can look for those as well. Like the fan in the background, obviously that's running on AC, but I think what we're starting to see more of are local, smaller DC systems, but it's very important to maintain a consistent voltage, so you need some type of computer or controller for that. So it's a good question. Okay, I want to show you one more thing here, if I can. This is my old computer lab. I don't know if I can show you that much. This is MIT, where I went to school, and I'll show you one of the things. I'm in Boston right now. I went all the way from Indiana yesterday. Now I'm in Boston. Let me just show you one other thing. I'll be right back. I've got to grab my phone. Hang on. Maybe I can find my friend too. Let's see. I'm just going down the stairs. It's the 4th floor. Here's the 3rd floor. There's the coffee house for coffee.
Yeah.
I'm looking for my friend. I don't see him. Second floor.
These decorations is probably gonna be $1,000, to be honest.
First floor. It's that's the bank. That's the grocery. Thanks. So, this is for a graduation. They're going to do graduation next week.
Oh, yeah.
Yeah, it's a tent, and that's the concert hall for music. A new statue behind me. It's a man.
Yeah.
It's a sculpture.
Yeah.
And you can see it's all numbers and letters.
Yeah.
Numbers and letters. It's made of steel. And then look, that's MIT behind me. So that's 77 Mass Ave. Very famous.
Sorry?
That's called 77 Mass Ave. That's the main door to MIT. That's the main door to MIT.
Okay.
This is where I went to school for my undergraduate. Okay. Okay. You should go to bed. Good seeing you. Thank you. And I'll see you maybe thank you.
Bye.
And maybe I'll see you again this week. We'll have to discuss it. Bye for now.